Hello. Today we're going to be talking about the optimal power flow problem, which is a very important problem in power system operation and planning. Um, so I'll guide you through some of the basic concepts, and we'll also address some of the solution approaches that we use in practice in solving some of these problems. So the outline of today's presentation will be really looking, as I just said, looking at the optimal power flow problem, why we do it, basic formulations, and what I mean by flavors, different variations of those formulations, and obviously what are the challenges and solution techniques. And then we'll spend a fair amount of time talking about the security constraint optimal power flow, well abbreviated SCOPF. We'll address it in its DC incarnation, and we'll look at some solution methods, namely here relaxation, and we'll look at a full-fledged example which will teach you how these things are actually solved in practice. So if you recall from our previous discussion of the economic dispatch problem, again, minimizing the cost of generation, subject to the power balance, and subject to bounds on the generation levels of the different generators. The main assumption of that problem was that the network is a solid copper bus in the sense that there is no network. So obviously in practice this is not true. We have to take into account the fact that there is a network. And even in cases where we effectively solve the economic dispatch, for instance, when we do dispatch every 5 to 10 minutes, there has to be a validation that the dispatch solution that we've just found will effectively be implementable over the network. So the idea of actually making sure that this set of injections is actually feasible, we need to actually solve a power flow problem, and then if there are some violations that need to be addressed, they need to be addressed in quote-unquote optimal way, and actually this would be solved using an optimal power flow problem. And also, again here, there's quite a vast amount of information that we need to also take into account. So there's several good reasons why we want to have a full description of the set of power flow equations. First, we want to have a more accurate representation of losses so that we can minimize them as much as we can. And also we want to be able to impose limits on generator reactive and apparent power outputs. Remember when we studied the performance charts of synchronous generators, well, these effectively define regions of operation. While the output of an economic dispatch problem might not be consistent with the performance chart of a synchronous generator, for example. Also, we want to be able to perhaps look at optimizing voltage magnitudes at generation load buses. And typically, this is associated with loss minimization. And also, we need to have limits on line flows in terms of either active power, apparent power, as well as in terms of current. So effectively here we're talking about some kind of thermal limits or stability limits in most cases. And also in most cases we've talked about in the context of the unit commitment problem, the idea of n-1 the n-1 criterion. And well, this is actually possible to be extending that concept to cases where we have a transmission network. So we have what we call operation under contingent conditions, basically making sure that our power system will survive the loss of some or a large set of components. So here, very often in the context of optimal power flow problems, we actually look at imposing security constraints, which we'll address a bit later as well. And also is that in practice, there is not just generation to dispatch. Yes, it's the primary lever of control, mode of control in a power system. However, there's there are many other control variables at our disposal, at least depending on the level, either from the operator or from the planner. So generated voltage levels, tap changers, um, phase shifting transformers, capacitor settings, static vars, compensators, etc., etc. So there are a lot more decision variables than available, or decision uh, vectors to be looked at, than just plain generation dispatch. So we are, most optimal powerful problem will include these variables as part of the bigger optimization. So when we look at problems, any kind of power system optimization problem where we have network constraints, these are called OPFs, optimal powerful problems. And they typically, again, they would find a minimum cost generation dispatch, um, making sure that all transmission system constraints are satisfied. And when we have security constraints, they will basically provide a preventive dispatch. So preventive dispatch means that it is a dispatch that we if a number of operating scenarios were to realize themselves, the dispatch that we have found would actually be still feasible with respect to the constraints whenever we enter different degraded states. Uh, and or also they could offer corrective measures for emergency situations. So we could have, as the result of an optimal powerful problem, a contingency, a plan to put in place if a given set of contingencies were to happen. Moreover, typically this is done over time scales which are slightly longer, is to look at periodic voltage and reactive power optimization, which again very often is related to loss minimization. They can also be used to look at um, determining how much power can be transmitted in a given system or in a given path. So we'll look at maximum loadability problems. And they can also be used to perform power system economic analyses, like determining incremental cost of generation or consumption at any node. This is something we'll be studying later on in the course. So as we had in our basic introduction to optimization in the course, we distinguish variables, control variables, state variables, parameters, uh, and here, so in terms of control variables, typically what we have here are things we can control, things we can play with that require a human or a machine to intervene in there. So generator set points, tap changer positions, reactive power outputs from static var compensators are very good examples. Whereas state variables in this case are arising from the actual model, physical model of our power system. And here again, we have no direct control over these. They are effectively byproducts of the implementation of the other control, of the actual control variables. So here we're looking at bus voltages both in magnitude and angles. Line flows are being another one example. Whereas parameters, so here which we'll denote by the vector y, these are characterizing the technical and economic structure of the power system. And typically, again, these things are known and assumed constant. So these would include generation cost functions, transmission line parameters, capacities, etc., etc. So the basic problem looks very, very close to what we've seen before. We're minimizing some function of the control variables, state variables, given a set of parameters y, and these are subjected to the vector function g of u x y equal to 0 here corresponds to the power flow equations. So these are equality constraints, as we've seen before, and h of u x y here greater than or equal to 0 represents all the other constraints inside a network. So moving on, so here going beyond the basic formulation. So again, optimal power flow problems will have some objective power flow equations, power flow equalities here as as necessary, and then some extra constraints on the other aspects of the system. So in terms of actual different variations over here over that theme, um, we're going to look at a few examples. So one of them is the minimum loss optimal power flows, where basically here we're trying to minimize the amount of losses in the power system. And to do this, we use the dispatch. So we're using the vector PG. We're also using the voltage set points at the PV nodes, so at the generator nodes, and that would be VPV. And T here would be the tap changer set points of the tap changing transformers. So you see here the two equality constraints are vector constraints in this case. So the first one would be the active power balance, and the second one would be the reactive power balance throughout the network. And H of all these variables being greater or equal to 0 represents all the other constraints on, be it state variables and or on control variables. Another very, let's say, famous version here is the security constraint optimal power flow, so SCOPF, which I've mentioned before. So here the key difference between what would be the standard optimal power flow is that we are indexing the different states of the system. So here we're indexing them using the index K, which can go from 0, 1 to all the way up to capital K. And here K equal to 0 represents the intact power flow case. So here that would be all generation and transmission assets are in. Then if you move on to K equal 1, then this represents number one degraded scenario of the power system. 2 would be another scenario, etc., all the way down up to the kth degraded scenario. And again, here they don't necessarily need to be power system degradation. You could also even look at these as being load or wind power scenarios. So what we're trying to do here, and what turn your attention to the objective function of the problem, and you'll notice that the objective function really depends on PG of index 0, and that would be what we would call the pre-contingency or the or the as forecasted generation cost, because this is the one we are sort of planning for, but making sure that this generation level is consistent with being able to operate in degraded conditions or post-contingency conditions. And what this entails is that all limits under both pre and post contingency conditions need to be satisfied. And the contingency conditions here is very important to see that the parameter y is actually also indexed by the contingency or the scenario index k to represent the actual state and or parameters associated with the operation of the power system in that particular state. The maximum power transfer, OPF, is also quite similar. So here the idea is that we're minimizing minus lambda, or effectively maximizing lambda. Lambda is a scalar in this case. And we're optimizing over generation, voltage set points, tap changers in that case. And basically what we're doing here, so you see that we are scaling up a vector of demands, both active and reactive. Again, you could decide to have different scalings, but the idea here is to increase, what this is trying to do is to increase lambda as large as possible until basically it's no longer possible to meet all these constraints. And effectively, you can see this as being example very something very similar to what you did in your in your power flow assignment, where you found the loadability, the maximum loadability in both P and Q sense of a given node. This is exactly what you did, but you did it in an empirical way, whereas here this actually you would solve an optimization problem to perform this. And obviously here you have different other versions that you could put together, including maximizing a specific flow. So for example, these kinds of problems are used to calculate in practice what we call available transmission capacity calculations. So they are trying to find how much transmission they can allocate to carry out transactions across different power system areas based on um, stability limits, thermal limits, etc., etc. So you would solve a problem like this to determine how much capacity you can actually allocate for these transactions over these interfaces. The DC OPF is effectively a special case of the original OPF, where the power flow equations are effectively the AC power flow equations. So doing it DC is great in the sense that it's much simpler to solve because the power flow equations are now linear and convex. Great stuff. And again, if your cost function is convex, and if your set h greater than or equal to 0 is also convex, then you have a guarantee of finding a solution, which would be optimal. So really here, and obviously you can also extend this to the security constrained version, which we will do later on. But the bottom line here is that very often you will solve a DCOPF first as a first approximation, and you might want to iterate around an initial guess for the solution found from the DCOPF to solve the full AC OPF. So what are the challenges with optimal power flow problems? Well, typically these problems are large because they need to represent a large number of nodes, lines, generators, so they have a large number of decision variables available. So there's a question of dimensionality. Because the power flow equations are AC power flow equations are nonlinear and non-convex, well, we have issues with multiple optimal solutions, slow solution convergence, and sometimes divergence. Um, and also, many of our control variables are effectively not continuous variables. So tap changers, tap changer positions are discrete. Circuit switching is an optimal power flow problem. Again, what should be the optimal topology to obtain, I don't know, minimum loss, maximum security, etc., etc. So these are 0, 1 type decision variables. And clearly now you're looking at a mixed integer solution technique needing to be put together. And clearly, in theory, the optimal solution can only be found through exhaustive enumeration. And as we've discussed with the unit commitment problem, this is clearly an issue when the dimensions become relatively large. And to go quickly over some solution methods, so for instance, graded methods are what we've looked at. We've mentioned them in passing before. You form the Lagrangian. You basically set the Jacobian, not the Jacobian, pardon me, the gradient of the Lagrangian function to 0, and you basically find from the Karsh-Tucker optimality conditions, you will find a solution. Uh, One of the key problems with that is that it requires that the objective functions, all the constraints, be differentiable. Uh, this is not always the case in practice. And these can be relatively slow in terms of convergence, and it might be a bit harder to handle inequalities because of complementarity conditions here. So here, this idea that the product of the Lagrange multipliers of the inequalities times the set the equation vector, the inequality vector h of ux y has to be equal to 0, while at the same time the vector mu has to be greater than or equal to 0. So this is what we've seen before. Same thing, Newton's method is the same idea, but again, being the problem that it's hard to handle inequalities. And clearly, well, linear programming kind of stands out here. Same thing with inter-point methods, but really, why is linear programming used with the simplex method effectively interesting? Is that, well, it's widely used in practice. A lot of the systems used in industry in the U.S., for instance, to carry out basic basic electricity market clearing is based on linear programming. Therefore, it has humongous practical implications here. And though the downside of this is that, well, we need to ditch the AC formulation to replace it with a DC formulation of the powerful equations. So clearly, we will lose some accuracy, but at least on the other end, we will gain solvability. So the one thing we also have to remember is that the simplex method, just hops from one vertex to another of the feasible space, and we have again very efficient and robust commercial solvers available like Cplex Group, etc., etc. And the industry likes it because, again, believe it or not, Excel has a very decent package to do linear programming within the spreadsheet. Interior point methods, you will see those being used for both linear and nonlinear versions of the OPF, and again, they are what we call barrier method, which penalizes the non-satisfaction of constraints as part of the objective function. But the idea is that the optimal solution are approached from inside of the optimization space up to the point when they get to the boundary. Relaxation. So the concept of relaxation is very, very important in the solution of large-scale OPF problems. And even now, not that I'm going to actually spend a lot of time talking about this, but I'll mention it in passing. Relaxation is currently what is the hottest topic in the solution of optimal powerful problems. So what is a relaxation? So a relaxation of an optimal powerful problem, or any optimization problem, is one that we solve an OPF problem which we ignore some of the complicating aspects. So clearly then, if a problem, which I'll call A prime, is a relaxation of the problem A, then the feasible space of A is a subset of the feasible space of A prime. So effectively, there's fewer options in the original problem than in the relaxed problem, which entails that the minimum that you will find for the fully constrained and the fully complicated problem A will actually be greater than or equal to the minimum for the relaxed problem, because the relaxed problem has more degrees of freedom, or the degrees of freedom are less restricted. For example, if we've talked about the 0-1 relaxation of mixed integer problems. So instead of having integrality 0 or 1, well, the value of a variable is able to vary continuously between 0 and 1. So we've basically rendered the problem easier for the solver to solve to find an answer. So here, how do we create relaxation? So again, the first one is to ignore constraints. Another one is to again replace discrete value variables into their binary version, or sorry, not their binary version, but their continuous versions. Other things would be to convexify the powerful equations. So some of you might hear about in the literature about convex relaxation, relaxations of powerful equations. This is something which is extremely very hot topic in the current state of research. So the idea about relaxation is that you start with a relaxed problem, you solve it, and then you check whether or not any of the constraints or features that you've relaxed out have been violated by solving the easier relaxed problem. If there are some violations, well, you need to bring them back in and then solve the problem again until you have no more of those violations. But really the key thing is that instead of having to solve one large, very difficult problem, you end up having to solve a sequence of usually smaller and easier problems than the big full problem. Clearly, there's a challenge here in terms of how do you pick the right amount of relaxation. So we call these, a tight relaxation will require, which is very, the problem that you're solving is very close to the original one. You've only relaxed a few features. It might require a few iterations because again, all of the complicating features will already be there. But again, it's going to be more difficult, and very often a lot of the constraints that you're carrying, and we'll talk about this later as well, we've mentioned it in class, but there are a lot of these constraints which will effectively be non-binding, especially in security constraint optimal powerful problem. On the other end, a relaxation which is too loose will require a lot more iterations. So obviously for you as a planner, you need to strike the proper balance to get the solution speed you require. And obviously here, knowing how your problem works and how its solutions being set will actually give you a lot of information about how finding the right relaxation. And clearly here, this is in the case of security constraint optimal power flow. This is extremely useful, and it's actually used in practice, and very often in some in the United States they talk about this idea of being called the simultaneous feasibility test, where basically you're taking your, a very good example is that the economic dispatch is a relaxation of an optimal power flow problem. So you take as your first guess is the as your first relaxation is the optimal is the economic dispatch, and then you check whether or not you are simultaneously feasible if that solution is simultaneously feasible for the network as well. And if not, then you can start adding constraints to the economic dispatch to get there. And this is what we'll do later on in this presentation. So the basic idea, the algorithm here is that you relax. Again, here we're only going to be relaxing inequality constraints. So we're going to set iteration index to 0. We're going to split our set of equalities I into a relaxed set and a non-relaxed set. So the relaxed one will not be considered, whereas the non-relaxed one will be considered. and these two sets have to be mutually exclusive. That's kind of obvious. And given that set of non-relaxed constraints, we're going to solve our optimization variable problem. So subject to the powerful equation in this case, and only a few of the some of the inequalities, so only those that belong to the non-relaxed set. We'll get a solution out of that, and then we're going to be checking for the relaxed constraints which ones have violations. So here, if we have a violation, if we don't have a violation, we go on to the next constraint. If we do have a violation, meaning that hi of uk star, xk star is, in this case, less than 0, then we will have to add the current relaxed constraint to the current non-relaxed constraint, and we update this, and then you do this until the optimal solution. You return the optimal solution that you have now. Okay, and you basically do this in a loop until you have no more violated constraints. And at the end of the day, you're sending your current solution in step 6. So in the case of the security constraint optimal power flow, we basically we have to reformulate. We're going to be reformulating this problem here. So we're trying to minimize the cost of generation in the precontingency state. So that would be the as forecasted, for example, state. And for each of the degraded states, including the precontingency states, we have to satisfy active and reactive power balances and power flow solution equations, actually, subjected to also other constraints. So here you have to realize that this block of equalities and inequalities is reproduced k+1 times to represent the power system in its k+1 possible scenarios. And here, what is important to underline is that this is a purely preventive control approach. You are trying to preposition PG in k equals 0 state so that it is actually feasible for all k equals 0 all the way through capital K. So it's quite conservative. It has to be feasible for all the states that you're considering. So to wrap up here, so we have a model system operation of k+1 possible states. We have the dimensions. So in terms of variables, we have k+1 states. We have m variables. So we have the same number of variables in every state, and similarly with constraints. So if n is the number of constraints, then we have to reproduce those constraints k+1 times. Clearly that, you can imagine that if you have a full AC SDOPF problem, this is going to start becoming quite difficult. So for the purposes of our of this course here, we will only look at the SDOPF in its linear form. It's going to be nice because, again, small examples will be able to be solved by hand, and it's going to also neglect anything that has to do with reactive power. And again, no matter what, it's actually used already quite a bit in industry, and it's easy to implement using off-the-shelf software, including the good old Excel. So if we look at the SDOPF problem, so it's formulated essentially in the same way. So minimize the cost in the 0th state. subjected to the power balance in k equals 0 to capital K states. And here we have this ck theta k plus F max minus ck theta k plus F max greater than 0. So these here are the line flow limits. And remember here, ck is a matrix that we've looked at the beginning of the course when we addressed the incidence matrix. Remember, ck here is basically the diagonal matrix of line susceptances times the incidence matrix transpose. So this basically calculates the angle differences between two nodes that are connected through an admittance, branch admittance, right? And here, so this is for the equations 2, 3, and 4. Equation 5, well, inequality 5 represents all the other constraints. And equation 6 here, theta rk basically is equal to 0, meaning that the angle at our reference is always 0. So when we look at this problem, so contingencies, so the different scenarios we need to look into might include generation and transmission outages, demand disturbances, changes in unforeseen changes in renewable generation, for example. But very important to realize here is that in the case of transmission outages, if you go back, well, you need to have B prime, the B prime matrix from the DC power flow, and the matrix C as being pre-calculated before the fact, because we need this information, so representation of the topology of the network and of its susceptance matrix beforehand. So this is an issue. It requires all of this to be pre-calculated and stored somewhere. Obviously, and also here, you can imagine we've already said that the problem by itself, before even considering contingencies, is a large problem. So imagine that if you are trying to solve this subjected to also requiring it to be immune to the occurrence of contingencies, well, we might have a problem. So it's very important that we try to keep the size of the number of contingencies to consider to be quite low. So clearly, in a practical system, even if we use what we call contingency screening techniques to try to weed out component losses that we know for sure will not affect the solution, because there are more demanding constraints or more demanding issues that might come about and that will effectively set the solution. It's still that the fact of the matter is that this formulation is still impractical for real systems, especially if time is an issue. You know, the idea of running an economic dispatch, running a powerful problem to check whether or not we have flow violations, for instance, or voltage magnitude violations, and then trying to find what should be the corrective measures to fix those. This needs to run very quickly because it's a real-time type application. Although we might have situations where an optimal powerful problem is used to model or to look at long-term planning issues, wherein the time solution might not be as much of an issue. So what we're going to be doing in the next part of this lecture, we're going to look at an approach based on relaxation of power balances and line flow limits as a way to solve this problem. Okay, welcome back. So in the second part of the lecture, we're going to look at elaborating the solution method by relaxation for a DC security constrained optimal power flow. So to give you right off the bat, we need to look at what's going to be the basic algorithm or procedure. And it will always start with the solution of an economic dispatch problem. Why? Because it's the easiest problem that we have at our disposal. Generally know that it's a convex problem. Therefore, we're going to be able to find a solution, and we're going to be able to find a solution fast and quite easily. Second step, we're going to look at the line flows in the intact network using a DC power flow approach. If there are any line flow violations in the intact network, given the dispatch that we found, well, we're going to redispatch the generators in the most economic way. And then after that, we're going to start taking components off the grid, one after the other. And again, the contingencies here will be loss of branches, meaning lines and or transformers. And we will be redispatching the generators in the most economic way. And what will be the true innovation here in this case will be how we will not have to recalculate everything every time. So we will not have to have a version of the B prime matrix for every possible contingency. Neither will we need a different version of the CK matrix for every possible contingency that we consider. And this is what we're going to be seeing in this second part of the lecture. So, what we're going to start by defining three what we call shift factors. So shift factors are, again, taking into account that we are in a linear version of the optimal power flow. Shift factors basically determine the impact of changing a power injection at the node and calculating its impact on a given branch. Okay, so the basic generation shift factor is, which we'll denote by the lowercase letter h, indexed by script L and I, and node I. So it's basically, when you look at this, it's the rate of change of the power flow on line L with respect to the power injection at bus I. So effectively, when we look at this mathematically, it's delta F, which is delta in the flow in line L to the delta in power injection at node I. Note though that when we change the power injection at node I, it has by definition, well, not even by definition, by necessity, any change at node I needs to be compensated in an equal and opposite amount at the reference node, at the slack node. So anything that we do at node I needs to be reflected in the opposite direction at the reference bus. And we can argue also that in the limit, as the change in the power injection at node I shrinks to 0, the top equality now turns into a limit, and we have a partial derivative of the flow in line L to the power injection at node I. So really what it tells you, it's the sensitivity of the flow in line L to the power injection at node I. And we'll see how useful that is. So why do we bother calculating generation shift factors? Well, is that we want to see what is the impact of changing the generation pattern on the network flow pattern. So, for example, the question that you could ask yourself is, what was going to happen to the flow in line L if generation at bus I is basically gone? right? So we have a loss of infeed due to a loss of generator. So obviously the assumption here is that if whatever we lose at node I gets picked up by the reference bus. So we have a slack bus there, and we have slack generator which can pick it all up. So if the generator at node I was already providing PI0, then the change in the injection of power at bus I is minus PI0. So the delta PI is minus PI0. So from this, then knowing the generation linear generation shift factor, what do we have? Well, we can find here the flow in line L after the fact, so that's why there's a little hat on F. Well, it's a linear combination of the flow with the original generation pattern, plus what happens when we apply to line L, so the shift factor times the change in injection at node I. So here in this case would be FL0 minus HLI PI0. So that would represent the flow in line L after the outage of the generator at node I. And effectively here again, this is for any L, any line, any branch in that network. So you can see here that just by pre-calculating the H's, we can effectively determine the effect of any change in injection at any node. So, and in general, because everything here is linear, we can effectively look at the simultaneous impact of changing generation at all the nodes at the same time. So here you see that we have the collective change in flow in line L due to having individual nodes changing their generation, right? And clearly here, by definition, the change in generation or change in injection, I should say, at the reference node is minus whatever everything happens elsewhere. And as a result, also, a very important thing to notice is that the generation shift factor associated to the reference node is always 0. Why? Because again, when you look at this, if you want to calculate H, if we go back to the definition, well, you could do a test where you inject 1 PU or 1 megawatt at node I, and you see by how much is the flow changed in line L. And the ratio of that change to 1 would give you the value of the shift factor. So here, and not to forget that whenever we have this plus 1 here at node I, well, there's an equal and opposite minus 1 at the reference. So in the case here with the reference node, why is it 0? Because we are injecting at the reference node and we are extracting simultaneously the same amount of power at the reference node. Therefore, there is no net injection in the network in this case, and therefore there's no net change in the line flows. Hence, all the H's are 0 for the reference node. And it's not uncommon to rewrite this in vector matrix notation just to make things nice and compact. So this is the post disturbance flow, F hat, the pre-disturbance, pre-outage or pre-disturbance flow, F0, plus H, a matrix H of generation shift factors times delta P, which would be a vector of injection changes. So how do we get the generation shift factors? And this is a very neat little derivation. So we know, again, from the DC power flow that we can find the angles, theta hat, at all the nodes except the reference, right? Exactly the same thing as before. So we're taking the inverse of the B prime matrix where the hat on the B prime signifies that we have removed the row and the column corresponding to the reference and slime nodes, which again, let's for argument's sake here assume that they're the same. So if we do that, take the inverse times the vector of power injections at all the nodes except the reference, that will give us the angles. We'll define now a new matrix X. So the matrix X as the inverse of the B prime matrix hat here at the lower n. We're going to just assume, and then we're going to pad it with a row of zeros and a column of zeros here. So when you look at this, so effectively the theta vector is 0 for the reference node, and the vector of non-reference angles, and this is here the vector of power injections, which here we have P1, or effectively you could call it P reference, and the vector of non-reference node injections. So clearly I can see that, you can see here that I can write theta, the full theta, including the reference node, as the matrix X times the vector P. That was defined over here. So X, so theta is equal to X times P. Also, since this is a linear model, well, again, if I apply changes in P, well, it will result in changes in theta. And clearly that if I let my changes in injections going all the way down to 0 in the limit, the rate of change of the angles with respect to the power injections is just a matrix X. Now, at the same time, again, when we've looked at the DC power flow, we had F of L was BL, so the line susceptance times the difference in voltage angles at both ends of a line. Or effectively the same thing, 1 over the line reactance times the angle difference. Quick question for you is to understand what are the dimensions of X. So the dimensions of B prime hat, in this case, would be n minus 1 by n minus 1. While X here we are adding 1 row of zeros and 1 column of zeros, so X is effectively n by n. Now, what we want to do is to consider the effect of a change in injection at node I on the flow on line L. So going back to the definition of HLI, so we know it's the partial derivative of the flow in line L to a marginal change in injection at node I. Well, we know what the flow is BL times theta J minus theta K. Apologies for that. Well, when I take the derivative inside the bracket here, well, I get BL, which is a constant, times d theta J by dpi minus d theta K minus by dpi. And what are these? So d theta J by dpi, well, effectively is the element x ji of that X matrix, and here d theta K by dpi is just element Ki of the matrix X, which we've defined before. So now we have one way to express H as a function of this matrix X. At the same time, when we look at this, so H, which is a matrix of these generation shift factors, when we look at this, it's as if we're taking d by dp of C, the matrix C times theta. Remember, C times theta, C was the diagonal matrix of line susceptances times the transpose of the incidence matrix. So when you look at this, C times theta is the same as having C times X. So effectively, if you have X, if you want to find the generation shift factors, we just multiply it by the matrix C. So if we remember here, F, the flows in a line, in all the lines is the vector of matrix vector product of C times theta. And this is where we recall what the definition of C was. Now, we had found that the dimensions of the matrix X were n by n. Now, what are the dimensions of H? So if you look at the indices of H, so we have the first index, which would represent rows, would be for the lines or the branches. So here we will have the number of rows of the H matrix will be equal to the number of branches or lines. And then what will be the dimensions in terms of columns? Well, here I runs from 1 to n. So we have an capital L by n matrix. So this matrix H is not square. Very important to not forget this. Next up comes in what we call the line outage distribution factor. Why do we bother looking at line outage distribution factors is the following observation, is that for every time we have an outage, or every time we need to model an outage in a security constrained optimal power flow, we would need to recalculate the B prime matrix, and we need to recalculate the C matrix. And this is again, this could be tedious, especially if we have a very large power system. So the idea of a line outage distribution factor is to effectively determine the impact on the flow of any line, call it L, due to the loss of another line, K. So the definition that we have here, so a line outage distribution factor, DL, given that we've lost K. So this is where sort of the mix of the notation here is the impact on line L given that K went down. So the ratio of the change in flow in line L following the outage of line K. So this is the change in the flow in line L. And we normalize that change in the flow to the pre-outage flow in line K, which we've just lost. Okay, so the use really for this is that if we know the flows on the lines L and K, so this is in the pre-outage state for both lines, while the post-contingency flow on line L following the failure of line K is going to be the original flow plus the outage factor, the line outage distribution factor times the pre-contingency flow in line K. So most likely we already have that answer. So we just need to calculate these and store them somewhere to be able to determine the impact of a line loss. So why do we use these? I've already mentioned them quickly, but that one of the main usages is to help system operators rapidly detect post-outage line flow violations. Again, there's no need to formulate those B prime and CK and C matrices for each contingency. All the information that we need is provided in the K=0 case. So there's no need to recalculate either B prime or its inverse for each contingency. And later on, we're going to see that we're going to be using the line outage distribution factors also to form compensated generation shift factors, which will be used in determining how we're going to be correcting dispatches when lines are out of service. So clearly here there's two ways to calculate or to represent line outages when we do an optimal power flow. One way is to again recalculate B prime and C for each outage. Obviously this is tedious, time consuming, and it might need to be sort of stored somewhere. And again, technically speaking, we need to have this representation if we're doing contingency analysis whereby we take out one component one after the other and find the resulting impact. However, in the second option, and this is really the clever one, and this is something that you might need to sit down and try to convince yourself here beyond what I'm telling you here. This is not an obvious thing. Well, the idea is that we can mimic that there's no flow on the line by basically making it believe that there's no flow in the line by having virtual power injections at both of its ends. And the advantage of this is that by doing so, we will not need to remove the line from the topology. So again, we do not need to recalculate the incidence matrix, the susceptance matrix, or the C matrix to calculate the what I call the K versions, in the sense the different representations of the network with and without certain components. So the second approach, albeit less intuitive, is much more effective in terms of use of computation resources. So let's have a look at how we're going to look at this. So here we have a network. So this is the entire network, and between buses N and M, there's a line K, and the line can be disconnected from the rest of the network by opening breakers at both ends of the line. So before the outage, there's an actual flow of power on line K, and we'll call it PNM. Obviously, if we open the breakers at both ends of the line, well, we have a post-outage flow here, which basically is zero. And effectively, there's no power going from the line to bus N now. So the topology of effectively of the network has changed, and line K is completely isolated from the rest of the system. So these are the sort of the key observations here. Now, what we're trying to achieve here is let's keep the breakers closed because we don't want to change the topology of the network. But what we want to do is to inject this virtual injections, delta PN, delta PM, and they're going to be equal and opposite to mimic the fact that the breakers here and here would be open. And then while this is happening, there would be a PN M tilde flowing in line K. So if we are injecting delta PN here and extracting delta PM here, and these two are equal and opposite and equal to this this PNM tilde, there's no current moving across those breakers. So this is an important thing to remember. So from the perspective of the network, this line would be completely disconnected. So let's have a look at what happens if we do that. So basically what we're going to do, we're going to inject delta PN at node N and delta PM at node M, and we're going to use exactly what we've already found before. So delta theta N, the change in the angle at node N and the change in the angle at node M can be found from multiplying X by delta P. So post-contingency flow will be the sum of whatever was flowing before plus whatever we are creating by having those virtual injections, delta Pn and delta Pm. So here we have Bk times the change in angles. So we're just basically plugging in what these are over here. And we're going to use the fact that X is a symmetric matrix because, again, the B prime matrix was already symmetric itself. And also the fact that the power injections are equal and opposite. So if we look at the fact that, so delta Pn, delta Pm are equal and opposite, and also if this is as if this network is isolated from the rest of the world, well, PNM tilde has to be equal to P delta Pn. So that's the key thing here. So effectively what we find is that we can go back here and we'll replace, we'll actually solve for delta Pn. That will give us what we want. Because really at the end of the day, Pn and M tilde is delta Pn because nothing is propagating to the rest of the network. So we can uniquely solve for delta Pn. And you see here, these only depend on pre-calculated values all from the X matrix. And here this is the pre-outage flow for this particular line. Okay, so one more step. We'll define new sensitivity factors, phi I and M, which basically tell us what's the impact on the angle at bus I when line K is dropped out. So here basically what we have is the change in the angle theta I when we normalized here to the line flow, pre-contingency line flow. So there's a number of cases that we need to look at. So first case, buses N and M are not reference. Second case, but bus N is the reference node, bus M is the reference node, and bus I is the reference node. And again here, it's a trivial case because in this case, if we change the injection at the reference node and we take it back at the reference node, there will be no change elsewhere in the network, just like with HL sub R. So here again, so direct substitutions from what we found previously in terms of delta thetas. And so effectively here we find the phi I given that NM is out. So two other cases. So here again, this is where N and M are not the reference bus. When N is the reference, when M is the reference. Again, clearly here you don't need to know this by heart, but you should understand where it comes from. And therefore, now from this I would get effective representations for the change in the angles due to the loss of FK0. So here, these effectively are the sensitivities we've just found, and from this, basically now we can actually have a closed form formula for the outage distribution factors. So clearly here you can look at the other cases and derive them as special cases. But rest assured that I'm not going to ask you to derive these from scratch, but you might need to have an idea of how it's actually performed. And last but not least, we have what we call the compensated generation shift factors. So then these are used to answer the following question. So what if we want to know the impact on the flow of line in line L when we modify the generation at bus I when line K is out of service or open. So we have a lot of things, moving parts in this case. So the flow in line L is influenced by the change in injection at any node I, delta PI, so direct, and it's done directly through the generation shift factor. And it could also be and also it's due to it's driven indirectly through the power flowing in line K, which would end up affecting the flow in line L when it's out. So what do we have? So now we have a change in flow in line L. Well, that there's a first portion which is due to the change in generation at or injection at node I, plus an outage contribution, so DLK, L given K, delta FK, which is the change in the flow after the correction. But we know that delta FK is just, again, the impact on line K of changing generation in node I. So in a sense, when we look at this, we effectively change the delta F to this over here, and we get our compensated generation shift factor. So definition here, we're going to use the Greek letter psi. So psi Li given K is the sensitivity of the flow in line L to changes in power injection at bus I under the outage of line K. And here the change in the injection at bus I has to be equally compensated for at the slack node of the system. Welcome back. So in the third and final portion of the lecture, we will look at the application of the relaxation approach to the solution of a simple security constrained optimal power flow problem. So here we're going to have to optimize the generation pattern of three generators, G1, G2, and G3, over a 3-bus 4-line transmission network. So we see here that we have 4 effectively electrically speaking identical lines, but with different flow limits. We have generators with minimum and maximum generation limits with a linear, strictly linear generation cost function. So here you see that there's basically just an A, what we use in the notation for the economic dispatch problem. We only have a linear component of cost. So what's going to allow is this actually is a feature that will allow us to use a linear programming approach. So the question we have to answer here is, what is the most economic n-1 secure dispatch, assuming we approximate the network with a DC power flow? So in here, by n-1 secure will be, we're not going to consider the loss of generators. We're only going to consider the loss of every single line. So we could technically write down the formulation of the full problem, right? Although again, if we want to solve this problem by hand, this is not going to be that simple. There's going to be a fair amount of work to do. So this is really what motivates the use of the relaxation approach. And it's going to basically require us to solve simpler versions of our problem by ignoring some of its complicating aspects. In the case here, we're going to be getting rid of constraints and bringing them back in only if they are effectively violated. So recall, so solve an economic dispatch, we're going to calculate the line flows, If there are line flow violations, we're going to try to fix those by redispatching generation. And in the fourth step, we're going to be doing the exact same thing, but when we are going to be degrading or taking out um, some of the transmission lines here, and we're going to redispatch to make sure that our precontingency dispatch will be able to survive the loss of any one branch in this network. And at the same time, we're going to see what's the impact on the cost of operating this power system as we are slowly but surely adding some of these constraints. So moving on, first step is to solve our economic dispatch problem. So if we look at the information from the startup slide here, so we have the generation data, we have the line data, and so we start by seeing that we have generator 1 at node 1, which would cost $20 per megawatt hour to run. The generator at node 2 costs $40 per megawatt hour to run, and the generator at node 3, G3, costs $50 per megawatt hour to run. And this is subjected to the power balance, so the sum of G1 plus G2 plus G3 has to be equal to 250. So again, going back to here, we have a demand of 200 megawatts at node 2, a demand of 50 megawatts at node 3, and no demand at node 1. So this is our power balance, required 250 megawatts. And we have generation limits for generator 1, generator 2, and generator 3. So clearly what we see is that we have a linear objective function, one equality constraint, and a number of box constraints here. So what we're going to do in the next few slides, we're going to look at what's the impact. We're going to actually try to solve this problem graphically. And again, knowing this is a linear program, we know it's going to have its solution will have to be at a corner of the feasible space described over here. And the other thing that I really want to draw your attention to, so if you are trying to minimize cost, when you look at this, you're going to try to maximize the use of generator G1 because it is the cheapest. So if we maximize, so trying to meet the power balance of 250. So if I look at this, so G1 needs to be above 100 and below 250. So when I look at this, well, G1 should be maximized, so I will increase G1 to its maximum, to the maximum possible, which is 250, which is equal to the demand. However, if we keep going down, we see that G2 has to be greater than or equal to 20, while G3 has to be greater than or equal to 0. So G3 can stay at 0 because we want to minimize its use because it's more expensive. However, G2 has a minimum of 20. So to be able to satisfy the constraints, we're going to have back down G1 by 20 megawatts and to bring up G2 to 20 megawatts. So here in this case, we have G1 producing 230 megawatts, G2 20 megawatts, and G3 0 megawatts. So let's have a look at this graphically. So we maximize the use of generator 1, and basically here, if we plot in the G2, G3 plan, and this is something we're going to be looking at for the remainder of the lecture, is to look at, so here the blue lines and the red lines here effectively are the box constraints for G2 and G3. And since we're trying to minimize cost, we're going to try to be as close as possible to the origin. And the other thing to realize here is that since it's a linear program, linear problem, the solution is going to be at either one of those four corners. And clearly here, the cheapest possibility is to have us running, as I mentioned in the previous slide, G2 at 20, G3 at 0, and G1 at 230. So this is the solution of the economic dispatch. The cost of running the Spire system in this dispatch solution is $5,400 per hour. Okay, so we're good. So first step is done. We need to validate whether or not this set of injections is valid. So clearly what we can do here is to calculate the B prime and C matrices, from which we will find the X and the H matrices. So here again, the B prime, this is taking the full 3x3 or 3 node network and applying the line susceptances that we have. And so as you see here that, the 5 minus 5, 5 minus 5, this refers to line 1, line 2, line 3, and line 4. And we're going to take node 1 to be our reference in slack. We're going to get X and H matrices after that. So here, X basically is the inverse of the block 15 minus 5 minus 5, 10 over here. And H will be C, the matrix C, times the matrix X. So if you look at an individual row of the H matrix, so here the first row corresponds to line L equal 1. And the first element here in the first column represents the sensitivity of the flow in line 1 to a unit power change, injection change at node 1, which happens to be the slack. So here we are injecting 1 and extracting it at the same location, so there's no impact, zero impact on the power flow of that line. Otherwise, if we now inject 1 megawatt at node 2 and extract it at node 1, we see that this actually creates a counterflow of minus 0.4 on line 1. And for the third case here, so this is we are injecting 1 unit of power at node 3, and we are extracting it at node 1, slack. And you see that this basically will create a counterflow of 0.2 megawatts in this case. We can keep up going this way. Oops. Okay, so let's do that. So here we're going to find the voltage angles. Although this is not necessary, we can actually go straight from the injections, P0, to find the pre-contingency or pre-fault line flows. Here 100 is there to signify the power base. So if we look at the injections, so at node 1 we have 230 megawatts, which we'll divide by the power base of 100. At node 2 we have 20 megawatts of generation, and we have 200 megawatts of demand. So we have minus 180 megawatts of demand, which in per unit would be minus 1.8. And then finally at node 3 we have 50 megawatts of demand, which we divide by 100, and this gives us the distribution of line flows on the 4 lines. And what do we see is that the third line here is over its maximum power of 60 megawatts. So we have a 6 megawatt overload on that particular line. Now the question is, what do we do? Now that we have 230 megawatts coming here, 20 megawatts from here, and we have no 0 megawatts coming from here. Well, the idea is that we're going to be So this is clearly a constraint which we've relaxed and which is being violated. So what we're going to have to do is to redispatch the generation, making sure that the flow in line 3 is less than 60 megawatts. So we will tighten the relaxation here by adding that constraint that it's missing. So how do we do that? Well, we're going to look at affecting the line flow in line 3 by changing generation at nodes 1, 2, and 3. So effectively, we can look at the flow in line 3 is the original flow before any redispatch happens, so that would be 66, plus the effect of changing generation at node 1, the effect of changing generation at node 2, and the effect of changing generation at node 3. So what do we have? So H31 times the change in generation at 1, H32 change in generation at node 2, and H33 change of generation at node 3. So we have 66, which is the current value, minus 0.2 times G2 minus 20, minus 0.6, G3 minus 0. And then you're going to ask, where's my H31? Well, H31 is 0, so we've omitted it. We have omitted it to mention it here. So effectively now F3 will be equal to 70 minus 0.2 times G2 minus 0.6 times G3. And this is really to reflect the fact that there's a reallocation of traffic among users. So effectively now, if we write the constraint differently, is to say that if we satisfy this constraint, then the line flow limit will be gone. So effectively what we need to do is to still solve our economic dispatch, but here we're going to add this extra constraint. So just to be clear here, this is a restatement of this constraint without decimals. So twice G2 plus 6 times G3 has to be greater than or equal to 100. And you clearly see that this is pushing generators to go above, to have a larger output to basically guarantee that we have enough capacity to ship the beer and everything else from the port. So if we look at what's the impact of this new constraint, well, what it does here is that it arrives, we draw it here, and it's everything that is above the black line, which means that the original point of operation has been taken out completely. So it's been cut off. Now the question is, now we have one more solution. So we could have a solution here, we could have a solution there, here, here, and here, and here. So really the question is, which generator should we use to relieve this overload? And clearly what we want to do here is to minimize the cost of having to do this. So if we look at the H factors of providing relief on line 3, so the line of relief, the rate of line relief in for generator 2 is only 0.2, whereas generator 3 it's 0.6. So by changing the output of G2 and G3, we are able to find solutions which are still acceptable for us. And you can see also here what is the cost of having to provide relief for this situation. Okay. So clearly here, when we look at this, in this case, so generator 3 is the unit which can within the constraint of its own dispatch, is able to provide the cheapest um, option. So we'll go with the cheapest option. Now we have this new constraint which has eliminated this lonely point there, and the optimizer tells us that this is the new operating point. And our cost in the process has gone up by $300 per hour. So now we can check if everything is in order, and so now we have um, generator G1, sorry, I forgot to mention, has had to back down by 10 megawatts from 230 to 220. This is picked up by generator 3, and generator 2 is still at 20 megawatts, regulating the mix. So clearly here, if we put in injections of 220, 180 megawatts, and here 40 megawatts, then we will be able to prove that all the lines are within limit. So the cost of doing this, well, is going to be the difference between the cost with the new requirement minus the cost with the old requirement. Then the fourth step, we're going to be performing the security analysis by knocking out components, and we're going to also have then look at what we're going to need to do if there are some violations. So here we're doing the N-1 security analysis. We're taking down lines one at a time and calculating the impact on remaining lines. And we can do this without recalculating everything by basically just use the test that Mrs. Scroggie test to check whether or not the lines are within the limits using the outage distribution factors. Okay, so let's have a look at the impact of losing line K equal 1 on the remaining lines 2, 3, and 4. So one way would be to calculate, use the matrix X to determine the sensitivities of the angles to changes in injections. So here's what we've done, and from this we find the outage distribution factors. We notice though that we can sometimes, in the case of this small example, actually infer those factors relatively easily. So for example, if we go back to the beginning here, and if we want to find what's the impact of losing line 1 on line 2, well, whatever was flowing here, now 2/3 of it will flow there, and so on and so forth. Whereas a third will flow on line 3 and minus a third on line 4. So we do this, we find the flow in line 2 when line 1 is taken down. So previously we had a flow of 80 megawatts, and now we have 2/3 of the 80 megawatts which was flowing on line 1, then flow in line 2 after the loss of line 1 is 133.3 megawatts, which is larger than its maximum allowable capacity of 100. And we can do the same thing for lines 3 and 4, and we actually find that line 4 is over the limit by 46. Is over the limit, sorry, it's actually under the limit whereas line 3 is above the limit, and we can see it in the picture. So this is beyond 60 and this is beyond 100. So we will have to do some redispatch to get rid of these two overloads. So how do we do this? We're going to find the flows associated. We can, oh sorry, this before we go there, we're going to look at the flows associated to the failure of line 3. We're not going to do it for line 2 because again it's a parallel line to line 1 and they're identical electrically speaking and capacity speaking. So here we're going to find the impact on line 1 of losing line 3. So we find that in that case, for losing line 3, whatever was coming out from before now from bus 1, which is 220 megawatts, will split half between the two lines and take us to 110 megawatts. So this is incorrect. This is not acceptable. And for line 4, we can do the same thing and find that it's just going to be 40 megawatts. So the question is, what happens if line 4 fails? I'm encouraging you to do it on your own, but the bottom line here is that nothing happens when line 4 fails. So how do we mitigate the overloads? Well, we're going to be redispatching the generation such that the flow on line 2 will be less than 100 megawatts, and the flow on line 3 will be less than 60 megawatts when lines either 1 or 2 and 3 are taken out individually, not together. So we're tightening the relaxation once more, and in this case, dealing with each contingency one by one. Why are we doing it one by one? Is because what we'll see later is that sometimes correcting for one contingency will also correct for another one for free. In a sense, you don't need to do an extra bit of work to make it happen. It's going to happen on its own. So to do this, we have to include now compensated generation shift factors, which calculate the impact of changing the dispatch pattern at node I on the flow in line L while line K is down. So if we're looking at the impact of the outage of line 1, or effectively line 2, because they are twins, identical twins, so it implies two flow violation, one on line 2, or line 1 if you're considering line 2, and the other one will be on line 3. So let's start with line 2 for the loss of line 1. So we have our inequality here, which has to be less than F2 max. And we need to calculate compensated shift factors. In this case, actually, we can derive them by inspection. If we go back to the power system, so here we're losing, we've lost line 1, and we want to know what is the impact of, for example, injecting one megawatt and taking at 1 and taking it out at node 1 is 0. But here, if I inject 1 megawatt or 1 per unit at node 2, how is it going to distribute across the system? Well, here this is susceptance of 5, susceptance of 5, susceptance of 5. So here this is a longer electrically speaking path, therefore more power is going to go through line 2 in this case. So we have to be careful here in how we approach these, not make assumptions. So here, going back, so we see that looking at line 2, having modification at node 1 while line 1 was down is 0, because again this is employing the slack node. The next one, we're using system 2 in with the loss of line 1. We find that in this case we create a counterflow by injecting at node 2, it creates counterflow of 2/3. And if we inject at node 3, we get a counterflow of minus 1/3. So therefore, we can rewrite our inequalities, and we need to make sure it's under 100 megawatts. So in rearranging the terms, we find that twice G2 plus G3 has to be greater than or equal to 150. So what do we do next? Well, we're going to add this constraint to the original problem, and we're going to, and that's it. So when we look at it now, so this new constraint now maps to the G2, G3 plane by basically excluding the point we found before. So now we have minimum the cost. This was the original constraint. This is the newest addition to the family, and we see that none of the kids that are on an IEP at this low have been assessed for an IEP over there. So we continue now with having this new constraint being added to the feasible space, which is there to limit the post-fault flow on line 2 when line 1 is down. So we see that we have this brand new constraint that has been added, which we've calculated before. So this is the second constraint. Now what we see also is that this constraint here is no longer in the picture, because now the feasible space is defined by this trapezoid. So if we perform the economic dispatch with this new constraint in, we find a new operating point right here, with G1 again losing generation, going down to now 175, G2 going up to 75 megawatts, and G3 to 0, back to 0. So G3 from before, if we go back here, previously in the previous dispatch, G3 add 10 megawatts over here, G2 20, and G1 220. And clearly here we see that we have increased our cost of generation. Now, verify that there's a statement saying verify that pre-fault limits are satisfied. They will have to be, because we know that pre-fault limits were over here, and we know that this is more demanding than this operating point over here. Now, and at the same time, is the post-fault flow due to flow limit due to line K going down, line K equal 1 going down within limit. It has to, but it's going to be right on it. It's going to be binding in this case. The next step will be to correct the effect of losing line 1, or equally line 2, onto line 3. So once again, we're going to formulate the flow calculation of line 3 with using generators 1, 2, and 3 to redispatch our system. And then here we're looking at differences or changes in the injection, and we need to make sure that this is within the confines of the transmission limits. So once again, we calculate compensated shift factors. By inspection again, we get that we have 0 for doing a change at the slack node as expected. minus a third at node 2, and minus 2/3 at node 3. And again, we should probably have a look at our network here. So we are looking at line 1 being taken out. So here we are injecting 1 megawatt at node 2, and we are extracting it at node 1. So when we have that 1 megawatt going here, we have twice the series reactance, and here we have one time the series reactance. So here we're going to have on line 3, so that 1 megawatt going in, being taken out here, will go through 2 times the reactance going this way. So therefore the bulk of it is going to go here. So we're going to have 2/3 flowing in this direction and 1/3 flowing in this direction. But you see that if you inject 1 megawatt here and extracting it there, it creates actually a counterflow of minus 1/3 in this direction. Similarly here, if we inject 1 megawatt over here, it's going to split between this path, so line 4, line 2 to bus 1, or the rest will go up in this direction. And we see here that again the impedance seen in this path is twice 1/5, so would be 2/5, and here it's 1/5, so 2/3 again by the same principle as current division. 2/3 of the power will go this way, and remaining 1/3 will go this way. And here there has to be a minus sign because this is creating actually a counterflow to the original flow we had in the system. So going back to where we were. Okay, so this is, as I just mentioned, this is the counterflow created by an injection at node 2, and this is the counterflow created by an injection at node 3. And so if we plug in those values over here with the current values of the dispatch G1, G2, and G3, we can basically, and limiting here to F max, F3 max being 60 megawatts, we can rearrange the inequality to say that this means that we need to have G2 plus twice G3 has to be greater than or equal to 120 megawatts. So the next step, we added this new constraint to the economic dispatch, same constraints as before, and let's solve it. So here we now see that we have a new constraint which has now chopped our original solution. So now the solution is here, 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 here. Or effectively we have how many corners? We have 1, 2, 3, 4 corners. And since we're minimizing cost, most likely it's going to be, the solution is going to be over here. So really, so this is the pulse fault limit on line 3 due to failure of line 1 or line 2. So now we have a new economic dispatch which now lies at G1 equal to 160, G2 60 megawatts, G3 30, and now the cost of generation has skyrocketed to 7,100. So this is our new operating point now. And clearly, as before, the solution, because this is a linear program, a linear problem, is located at a corner, at a vertex. So we want to make sure that everything is working with this new dispatch. And last but not least, we want to find, because we had a third violation, which was the effect of losing line 3 on line 1 or line 2. So once again we can go back to writing the flow in line 1, given what is the flow in line 1 when we lose line 3, and using the shift factors, the compensated shift factors, to enforce this new constraint. So here, again, going back to our power system. So if we lose, in this case, we lost line 3. So if we have anything coming into node 2 being taken out at node 1, line 1 and line 2 are identical, so the power is going to split half-half and 50-50, and we're going to have a negative power flow. And here again for node 3, we inject 1 megawatt. It's going to split 50-50 again towards the slack node over here. Okay, here we are. And making sure that this is less than 100 megawatts, which is the limit on lines 1 and 2, we get that G1 and G3 together have to be at least 50 megawatts. So let's add this to the picture, and you clearly see here that this line limit is not very demanding in comparison to the two that we had previously on lines 2 and 3 due to the loss of line 1. So we see here that this magenta line is going to be completely inactive and completely useless in this case. So what's the generation dispatch? It's exactly what we found before. So it is as we found by correcting for the loss of line 1. All the constraints aside the green and the cyan one, which are over here, are inactive. So in fact, they are redundant. And so is effectively also the pre-fault flow on line 3. And so these, what we've seen also appearing in the literature recently is this notion of umbrella contingency, because these are failures or bad events that happen which are so severe that if you take mitigating measures against those, they will actually create umbrellas over lesser severe or less stringent failures. So this is usually a nice side benefits that you get. So correcting for the loss of line 1 or line 2 was able to correct for the effects due to the loss of line 3. So we're getting to the end. So the question is the final economic dispatch secure with respect to all the pre-fault line flow limits, all the post-fault flow limits? So here if we have, now this is the final dispatch, 160 megawatts here, 60 megawatts here, and 30 megawatts here being injected. So here the full 160 has to split. So we have 60 plus 60, that's 120, plus 40, that's 160. So it splits like this. Same thing here. So again, here the 200 megawatts is not fully supplied. So we need to have so 120, 140 coming to make up for the missing power. And then here at node G3, we'll have the 20 megawatts extra coming from G1, and whatever is left keeps going to node 2. And if we lose the any line, so line 1, so here if we lose line 1 or line 2, well, my line here is still capable of taking 100, still capable to push 60 down here, and we're capable of maintaining secure operations. So here you see that we had 2 lines which are effectively binding. So this might be a bit of a dangerous situation in practice, but again, for the sake of this example, we won't discuss that. What else now? If we lose line 3, we see that we have that 160 megawatts, which gets shared 50-50 between lines 1 and 2. There are no overloads. Notice here that the flow of line from 3 to 5 has actually flipped in this case. And then finally, if we lose line 4, and this one here, there's actually no binding constraints. Same thing as over here. Okay, so all limits and our constraint, our limits are met. The algorithm terminates, and then the question you can ask yourself is, what is the cost of security? Well, the cost of security here is the increment in cost from the original economic dispatch problem. So how much did you have to pay extra to make sure that if any of those line limits is violated, you had to redispatch? What is the cost of that redispatching? And we call this the cost of security. It's the delta cost between economic dispatch, well, not sorry, I think a security constraint optimal power flow and a basic economic dispatch. So thank you very much for your attention, and please feel free to forward your questions to me by email or in person in class.